So let's get back to where we kind of left last time. Yeah. So we have been talking about this operational amp integrator circuits, and how this kind of evolved. The storyline was we had a inverting amp first, right? And then from there, we created a integrator by just swapping a resistor to a capacitor. So if you see from here, we had an inverting amp like this, and we have swapped this resistor into a capacitor, and from here it's integrator, right? And this to be on. And we talked about some practical limits. For example, in the very low frequency, it's going to hit almost infinite gain. So that's not good. So we introduced a practical op-amp integrator by having a resistor connected to it. So practical integrator, right? And this parallel resistor or shunt resistor was applied so that we can still maintain this feedback loop, all right? And for that practical integrator, we talked about this graph where this line here is the ideal integrator frequency response. And the problem was in the very low frequency, when the excitation frequency is almost like 0 hertz, or when it's like a DC, then this shoots to infinite, which is not possible. We cannot have infinite output in real life. We can have 0 output, right? But we cannot have any infinite. And when we start to see something infinite, generally you have some problem there, okay? So this part, the amplitude goes very high, so that was a problem. So we use this practical thing to chop that response down, and then it kind of converges to the infinite, the ideal response as the frequency rise up higher and higher and higher, right? However, by utilizing this this practical circuit, it kind of solves a problem in this low frequency at the expense that this low frequency range, okay, because just visually you can also see this is the ideal response of an integrator and this is the practical response. They are different, right? Ideal integrator really like integrates, but our practical thing is different, so it does not integrate. However, after this frequency of the cutoff frequency, they kind of converge, right? So we can assume our practical response is similar to the ideal case. So it integrates your input and your output becomes a different waveform, right? And in case I have a choice of these frequency range, then I would like to use a frequency that is higher, even higher than the cutoff frequency, about like 10 times higher. But I'm not going to use too much high frequency because in this regime, V out is getting smaller than my Vn. So I'm losing some power or amplitude that I already provided. Why would I want that? So I'm going to be using a frequency range that is between here and there, where I can still have a lot of juice coming out and it's going to be integrated. As you can see, when it is right above this cutoff, our ideal and practical, they're kind of getting closer, but still there's a little bit of discrepancy. So that's the reason why I don't want to use. If I push this a little bit higher, then they really get close. So my practical and ideal, they're almost the same. So That's the reason why, okay? And that's what we talked about. And we would like to try a simple example problem so that it may help this understanding, okay? So the problem here is we are given these values, RS, CF, and RF, all right, as these. And our input was a sine wave with 5,000 hertz, okay? And the question is, how would the output voltage look like? So first step may be check whether your excitation frequency is within that suitable range for integration. What I mean is whether it's within this kind of range, okay? So in order to find this, we need to find 10 times of cutoff and the 0 dB. So first, let's try this cutoff. So FC is 1 over 2 pi RF CF. All right. And if we do the math, say RF was 100K, so this is 100 10th to third, and CF is 10 nanofarad, so 10 nano is 10 to the negative 9, right? So if you plug those in here, then we'd be able to get about 160 hertz. Okay. So from here we can say that for proper integration, the excitation frequency, excitation frequency should be greater than 10 times of FC, right? And that is going to be approximately 1600 hertz. So we just got this portion in the unit of hertz. So it's going to be 1600. And we need to find this guy, right? Which is 0 dB frequency. So F naught is 1 over 2 pi R S CF. And we have our RS is 1K, so this is 1000, right? CF is same 10 nano, so 10 to the negative 9. And if you do the math, it's going to be 16 kilohertz. So by combining these two, 10 times FC and F naught, what we can tell is 10 times FC was 1.6 kilohertz, right? And F naught was 16 kilohertz. And between those two, we had kilohertz, which is our excitation frequency omega, right? So visually, this guy here is 1.6K. It's 10 times of omega C, right? And this guy is 116 kilohertz. And our excitation omega is about 5K in between somewhere. So we can definitely tell the practical response that follows the black line is almost same as the ideal line, right? So we can say suitable for integration. So since our excitation level that falls between these two range, practically speaking, our output our ideal and this practical response are identical. So the output voltage of our practical circuit is same as ideal response. And our ideal response was V out at time 0 minus 1 over Rs Cf integral times 0 to t Vn of t dt. And where did I get this equation? I got that from our previous derivation. It's the ideal response, right? So we had that derived at the very first day, this guy. So it's here, right? And so I have just, oopsie, it's rewritten down here. Okay, and let me see. Oh, I didn't make that assumption. So if we just assume this guy if we assume this initial output voltage to be 0, just to make life easier, then all we need to do is just solve this guy, right? And continue doing the math. It's 1 over Rs was 1K, so it's going to be 1/10 to the third times Cf is 10 nano, so 10 nano is 10 to the negative 9, right? And integral 0 up to t. Vn was 5,000 hertz sine, so sine 2 pi 5,000 t of dt, right? This is just pure math. And we do this is 10 to the third, 10 to 9, so this becomes 10 to 6. We have one more here, so that guy goes up. So negative 10 to the 5th divided by 2 pi 5,000. And sine changes to negative cosine 2 pi 1,000 t, right? So this whole thing changes to negative cosine and 1 over 2 pi 5,000, right? When we do the integral. So after we do the math, this has become positive and things go away. And that is going to be 3.18 cosine 10,000 pi times t. Okay, so we had an input that was sine 2 pi 10,000 pi t, and that has changed to a cosine with the amplitude is 3.18. Okay, and if we assume this is our Vn, then our V out is going to look like, try my best. Write this one down, so it's a cosine like that. And it starts with a value at 3.18, right? Because our amplitude was 3.18 and this is a cosine. So one thing we can clearly see is we had a sine going in and our output changed to a cosine. Okay, so the waveform has changed, sine to a cosine, right? That's what we kind of expect. And look at the amplitude. Because it is within the suitable range, your amplitude is greater than 1, greater than your input amplitude. We applied input that had an amplitude of 1. And the reason why we want to use this suitable range is we don't want to lose any amplitude in it, right? So from here, we could see that, oh, our output was actually greater than our input amplitude-wise. So we didn't, miss any power or anything like that. Okay. And one thing that I just want to, make sure is by using this integrator, like whenever we do the integration, we want waveform change. That's what we kind of expect. Okay. Say for the inverting or non-inverting amplifier, if you had a triangular going in, your output is triangular. It may be just amplified, or it may be flipped over, but triangular goes in, triangular come out. If you had a square going in, square coming out, that's the amplifiers. But for these integrators, if you had like a triangular going in, you want something else come out. If you had like a square come in, go in, you want something else come out. Okay, that's what we want to have. Okay. So now we would like to talk about the differentiator. So, integrate, differentiate, they are complement to each other, right? It's like a mirrored thing. So the configuration of the circuit is actually like very intuitive. We are changing the opposite thing. So again, same story. We had an inverting amplifier, right? This is inverting because you can clearly see your input is going into the negative input node, right? And for our integrator, we swapped this guy to a capacitor. But now we are replacing the resistor from the input to a capacitor here, okay? Previously, there's a diagram. This guy was the thing that we changed, and that made an integrator. And now we are changing this serial resistor to a capacitor. So it kind of, makes sense. Like differentiator integrator is the other side of the coin, right? And I'm not going to do this here, but because I've done this like I think 7-8 times by now. We do the ideal op-amp, use this 3-step, right? Use the ideal op-amp conditions and do the KCL at this negative input node. KCL is what? It's flow in is flow out. So these two are flowing in. That is same as the amount that flows out, right? And then if you find the I's, the current values of all these points, and just use all these conditions, then you will be able to derive your equation, okay? And this is not just for the integrator, differentiator, amplifiers. It's whenever you are having a circuit that has an op-amp, these 3 steps can be utilized, and it really, for 95%, more than that, you will be able to get the governing equation or understand how it works. Okay, so after we apply all these 3 steps, our output voltage V out is negative RF CS ddt of V in. And from here, we can clearly see our input is being differentiated and it's being multiplied by some gain, and you flip the sign, and that's our output. So our derivative is proportional to our output, right? So that's the reason why it's a differentiator. And V out is, again, proportional to the derivative of VI. And compared to the integrator circuit, this can be regarded as, it's not much used in practice. It's being used, but it's not that much used compared to the integrator, since tends to amplify noise. Okay. And for the integrator, I talked about that kind of 3 steps to guesstimate how your output may look like. If you go back to here, getting output, first do the integral, flip the sign, amplify some signals. So even though you don't do the actual math, you can kind of estimate how your output is going to look like. Okay, we can do the same thing for this differentiator. So for example, say we had an input that's a triangular wave like this. Then from here, we can just naturally estimate how the output is going to look like. So step number 1 is derivative. Step number 2 is flip the sign. And step number 3 is we apply some gain, RF times CS. Say, because these 3 steps is something not you need to really memorize, but it's just naturally doing these 3 things in series. So I first find the derivative and then multiply with some number and then flip the sign. Okay, that's what we have here. Okay, so let's try this thing. So from here to there, it's a constant kind of motion. So what's the derivative of this ramp? What would be a derivative of a ramp? Yeah, it's going to be a straight line or a constant, right? So, and this is a positive ramp, so it's going to be a positive straight line like this, right? So that's first step. So let me, like this. And then we flip the sign. So this is a positive straight line. So I just flip the sign, and then that becomes a negative straight line. So this just goes away, right? So I originally had a derivative. This is a positive ramp, so it's a positive constant. Flip the sign, so it's a negative constant. And then multiply RSCF. I don't know what the RS and CF are, but probably it's going to amplify this or maybe shrink it down depending on the value, right? So it's going to be a constant line that moves like somewhere, maybe we can count it like it's going to be down here. So that's amplified down like this. So that's the final answer we got. So again, it's a positive ramp. So the derivative is a positive constant. And the next step is we flip the sign, right? And we multiply some number. So I just assumed it's going to be greater. So now in a line like this. What about this part? It's a negative ramp, right? So it should be a negative constant. You flip that over, it now becomes a positive constant. And from there, you multiply some gain. So maybe it's going up like this. Same thing down here. See? So we can roughly estimate how the waveform shape is going to look like. We don't know the exact value of these, right? Because we don't know what RF is. We don't know the slope is. But just by looking at this waveform, we can estimate, oh, probably it's going to look like this. And it's very natural following what I mentioned. We want the output waveform to change. You see, I'm applying a triangular in it, and what I'm getting is a square. So the waveform has changed, right? How about we try this one together? So can anybody tell me how the waveform would look like in the output if we provide an input as this guy? What's the output going to look like? So if we focus on this, by the way, it's going to be a straight line, yeah. Because here is a constant, right? So derivative of a constant is 0, right? This guy too, derivative of constant is 0. And we do the 3-step, it's going to be the same because the derivative of a constant is 0, right? So we have 0 here. And then we flip the sign, it's going to be still 0. And we multiply some number, it's going to be still 0, right? So it's 0 here, 0 there, 0 here, 0 there. But this part, we can think a little bit more about that. This here, what's the slope of this guy? It's a negative infinite slope, isn't it? It's dropping, right? So that should be a negative value, very large negative value here. That's the derivative. And we flip the sign. So this guy goes up. We flip it over. And then to this value, which is infinite, we just multiply something. It's still going to be infinite. So we're going to have a spike that looks like this here. That makes sense? What about this part? This is a positive infinite slope, right? So we have a positive infinite derivative, and we flip the sign, so this guy goes down, and then we multiply something, so it's still just going to be an infinite spike, like this. Does that make sense? Yeah. So the usage of these differentiator circuit is that we can find high frequency content of the input, or it's going to be used as an edge detector. So say let's take a look at this one. So from here to there, it's changing, it's rising up, right? But it's slowly rising up. I mean, or it's not changing that much. I'm rising today a little bit like this, tomorrow a little bit like this. So there's almost kind of no abrupt change. It's just doing everything same every day. But suddenly, from here to there, I change the direction, right? So this part is a relatively abrupt change, isn't it? I used to go like this direction, suddenly I changed to there. So this part is a high frequency content, or it's just changing immediately. Changing immediately, that is like high frequency change. So these parts can be detected by using these differentiator, because here it's a sudden change. You can see there's a sudden change in the response level. Or it can be used as an edge detector, same thing. For example, here is something, and then it changes the edge to down here. So this part can be regarded as an edge of some kind of level, right? So this part is detected by that sharp transition or a spike in our output. So by looking at this output, we can tell, oh, something is suddenly changing here, or something is suddenly changing here. It's like an edge detector, okay? And I'm not sure whether this is being used in that area, but edge detectors are very often used for signal processing, and these days AI, image processing, those kind of things. Like we want to detect a car, you know, from the background. So looking at this edges, right, that kind of tells something is there. Okay, so this is one of the applications that might be used, but you know, it's probably in this area it may be used as in a software way, but the circuit is very often used as an edge detector. And because I said differentiation tends to amplify noise, it's practically, it's not going to look like this, but it's going to look like this. It's going to be looking very hazy. Like that. Okay. Although we don't have almost no noise at all in the input, that still, it might have a very small noise, right? That guy is being amplified and it's showing up in your output, but still it kind of maintains this waveform. Okay. Any questions you have? Okay. Then let's move on to the frequency response. So the frequency response, we use the impedance analysis, and that is going to be same negative ZF over ZS. And we need to find out what our ZF and ZS are. And this guy here is ZS, and this guy here is ZF. So ZF is nothing but a resistor, ZS is a capacitor. So this is negative RF over 1 divided by J omega CS. And it's going to be negative J omega RF CS, just like that. Alrighty. And we would like to do this extreme case analysis again. So let's assume our input was a DC voltage. In other words, the excitation frequency is very small or 0. Then what would be the output over input amplitude ratio for this differentiator? What's going to be the value for that? What was that? Why do you think so? It's this one. That's the response of this guy. So if we apply omega is 0 to here, right? This is going to be 0. So the whole thing is 0, right? So output over input ratio is going to be 0. And we have this magnitude, so we ignore this negative sign, right? And what about the AC with a very high frequency? Then omega is very large, or we can tell it's infinite. Then what's the output over input ratio? Yeah, it's going to be infinity. Yeah. So if I draw the Bode plot just one more time, then in decibel unit, this H magnitude, the horizontal axis is the frequency in log scale, then it's going to go up straight line like that. Because initially, when the frequency is small, it's going to be 0, or in other words, in decibel, it's going to be negative infinite. Then it's going to rise up, rise up, rise up, and then at the very high frequency, it's going to be positive infinite. And which area is going to be the problem? The low frequency or the high frequency? High frequency, right? We can always have our output to input ratio 0, because if our output is 0, then the ratio is 0, right? So it has no problem, just the output is 0. But we cannot have our output to be infinite. It's blowing up, right? Or it's very nice because we can have infinite power coming out, right? So this is something not so good. And if we move on, have the same story here. Practical op-amp differentiator. And what we're doing is we would like to introduce additional resistor next to the capacitor. And if we do transfer function one more time, that's negative ZF over ZS. And we could count this whole thing and this whole thing as ZS and ZF, right? And ZF is nothing but RF, and ZS now is going to be two impedance in series, right? So it's going to be just adding those two. And so RS plus 1 over J omega CS. So if we apply these back into our equation, Z over ZF over ZS, then the transfer function is going to be negative RF. This is ZF, right? And this whole thing goes down here. So it's RS plus 1 over J omega CS. And if I just write this down one more time, it's going to be J omega RF CS. And this is 1 plus J omega RS CS. Okay. And by the way, we have that same assumption. RS is going to be much smaller than RF. That's the assumption when we apply additional resistor. So with this practical op-amp circuit, one more time, if we do that frequency analysis for the extreme cases, if our input were DC or very small frequency input, in other words, this is 0, then what's going to be this output over input ratio? Yeah, 0, because this is 0, this is 0, so 0 over 1 plus 0 is 0, right? So this is going to be 0. However, when the frequency is very large, or it's going to be infinite, what's going to be the value? Negative 1/2, like this. Maybe you can try one more time. Negative 1? Oh, no. This is actually, so this guy is infinite, right? And this guy is infinite. So we can ignore this 1, right? It's just very small value. And we can get rid of CS. This is left. RF over RS, because infinite, they go away. And this is going away as well because we have this magnitude sign. So it's going to be RF over RS. All right. So this is practically a high pass filter with amplitude gain. That's not what we are really interested in. We are interested in the integration performance. So if I draw a body plot, this is log frequency, and this is H magnitude in decibel scale, and here is value 0 dB. And our ideal case look like that for the differentiator. If you remember from the previous page, it was going up like this. And this part was the problem because it shoot up to infinite. The high frequency is the problem. But now our high frequency is limited by certain value. It's a finite value now. So the practical response may look like this. So this is ideal case, and this is practical. And the level it gets saturated, this value here is going to be what? RF over RS. Because in infinite frequency, when the frequency is very large, its value should be what? RF over RS. But by the way, because we plot that in the unit of decibel, we just convert this into 20 log base 10 of RF over RS. Right? And same thing here. This is the cutoff frequency, and this is the 0 dB frequency. And similar to our integrator circuit, which frequency is the frequency you want to use for differentiation here? What frequency do you want to use? What was that? 10 times WC is here, right? So you want to use the frequency here? No? Or, oh, what was that? Yes, so lower than this, but above this guy. That's where I want to use for the same reason. If you go, so the practical response is getting close to the ideal below this frequency, right? So here is where we have, this is where we have differentiation working. And this is not differentiating at all. And we don't want to go too low frequency because the output is getting smaller and smaller than our input as the frequency gets lower. So we're kind of losing power. You provide like 10 volts in, you only get like 0.5 volt coming out. You're kind of losing power, right? So we don't, in general, we don't want to use this frequency at all. So we may want to use somewhere between here and there. And if you had a luxury of choosing the frequency, then I would go 10 times lower than the cutoff. So the cutoff divided by 10 times, that's where I would like to use. And I would like to go above my cutoff, my 0 dB. So this would be the frequency range that would be kind of the best you want to use for differentiation. Okay. One more time. This red line is the ideal case, right? And the problem here was when we have a very high frequency, the ideal output amplitude blows up to infinite, and this is not good. We cannot have this. So we introduce a practical response that chops this thing down to a finite level. However, by chopping this down, we are kind of losing this frequency range because our ideal and practical are different. So that means our practical circuit is not following an ideal response at all. Only this frequency range, frequency that is lower than cutoff, only follows the ideal response. So here is kind of the range you want to use for differentiation. However, I don't want to go too down, too low, because if you pass this 0 dB, then your V out is getting smaller than your V in. So you're practically losing power. So I don't want that either. So I would like to be between these two. And here is going to be kind of the sweet spot. Okay.